Okay, back to work here. Working on 11.8, homework set on Lagrange multipliers. So I'm going to start off, I'm going to do number 1. So for number 1, we have a function of two variables, f of x, y, equals x squared plus y squared. And then we have a constraint that x, y must equal 1. X times y must equal 1. All right, so we're trying to find the maximum and minimum values or minimum values of this function, but we are constrained to this curve x times y equals 1. So what we're going to need to do is we're going to have to check where the gradient of f is equal to lambda times the gradient of g. So I'm going to set up the gradients. This is the only time I'm going to show this because this is done in the lecture. I'm going to take the partial of f with respect to x, partial of f with respect to y, create a vector from that. That's the gradient of f. I need that to be equal to lambda times the gradient of g, which is this. And then I pass the lambda through. I get lambda gradient of g, gradient. Lambda times the partial of g with respect to x. Lambda times partial of g with respect to y. That must equal this. And then I set the components equal to each other. So I'm going to set this equal to this, and this equal to this. That'll give me 2 equations, and then this will be my third equation. So my 3 equations are as follows. First equation that I need to satisfy is that the partial of f with respect to x must be equal to lambda times partial of g with respect to x. Second equation I have to satisfy is the partial of f with respect to y must equal lambda times partial of g with respect to y. And the third equation is that x, y must equal 1. So that's the constraint. Remember, this side right here is your g of x, y equals some constant over here. All right, so now the partial of f with respect to x is just 2x. Partial of g with respect to x is y, so I'm going to have lambda y. The partial of f with respect to y is 2y, and that must be equal to lambda times partial of g with respect to y, which is just x. And then my third equation I'll leave alone. All right, so if I can find an x, a y, and a lambda that make all 3 of these true at the same time, then I'll be done. I'll just check those values into the original function, see which one gives me the max, which one gives me the min. All right, so a couple of options here. How should we do this? How about this? How about we try and solve each of these for lambda and then set them equal to each other? So how about this? I take my first equation here. Okay, working with equation 1, I know that 2x must equal lambda y. Now, if I suppose here that y is not 0, then I can divide both sides by y and get 2x over y equals lambda. Similarly, if I suppose that x is not 0, then I can take equation 2 and divide both sides by x, and I get 2y over x equals lambda. So remember, I'm supposing 2 things here. X cannot be 0, and y cannot be 0. Assuming those 2 are both not 0, then lambda's this, lambda's that, set them equal to each other. I get 2x over y equals 2y over x. And then I can multiply both sides, cross multiply if you want to say that, that's fine. You get this. And then divide by 2, you get x squared is y squared. And then take the square root on both sides, and you get x is equal to plus or minus y. So you're either going to have x is equal to y, or x is equal to negative y. Now, if I go to equation 3, let's suppose x equals y. So let's suppose this one. if x equals y, I'm going to replace the y with x. We get x times x equals 1, x squared equals 1, which means x equals plus or minus 1. So what we're going to get here is that if x and y are the same, then x is either positive or negative 1, which means that y is equal to positive or negative 1. So look at the way this works. X has to be equal to y. So if x is 1, I'm going to write these down. If x is 1, then y must be 1. If x is negative 1, then y must be negative 1. That's what these two things are saying. And I can actually get lambda from this also. Remember, I like to write these things x, y, lambda, just so I can figure out what they are. Let's say that x and y are both 1. I can come back over here. If x and y are both 1, lambda's 2. And if x and y are both negative 1, then again, lambda's still 2. So far, these are my points of interest without the lambda. Lambda is just there to help us solve the three equations. Okay, that was if x was y. What if x is negative y? So I'll do that right up here. Suppose x is equal to negative y. Then this third equation becomes x times, and then this will be negative x, equals 1, which means negative x squared equals 1. And there's no way that that's ever going to happen. So that's never 1. So I can throw that out. Okay, this won't happen. All right, so we assumed here in the beginning that x and y were both not 0, and we got these results. Now let me go back and say, okay, well, what if x was 0, right? Then what if y was 0? So let me try this. Starting a new train of thought here. Suppose x is 0. If x is 0, equation 1 becomes 0 equals lambda y, which means that lambda equals 0 or y equals 0, right? Set each of those equal to 0. So let's look at those two cases now. Suppose lambda 0. If lambda 0, equation 2 becomes 2y equals 0, because this is 0. And that means that y has to be 0 also. So if x is 0, lambda could be 0, which would mean y has to be 0. Another thing I could do is suppose y is 0. If y is 0, then equation 2 becomes this one. Well, actually, let me go to equation 2. If y is 0, you get lambda x right here equals 0, which means lambda is 0 or x is 0. But x was 0. Remember, if x was 0, then lambda could be 0. Y could be 0, and if y is 0, both x and y are 0. Right? That's what I have right now. X and y are 0. So I get that they're both 0. Right? If x is 0, then that's going to force y to be 0. And I think I can stop here. I could go now and say, suppose y is 0. If y is 0, I'm going to go through the same thing and get the same results. Just things are going to be switched up a little bit. So I do have one more important point to look at, and that would be if x and y are both 0. By the way, notice that if x and y are both 0, my third equation, right? The third equation, so suppose x and y are both equal to 0, then a third equation becomes 0 equals 1. That's not true. So I can't satisfy the last equation if I let x and y be 0. So I actually don't want to look at those points, or that point. So those look like the only two critical numbers. Let's see here. Okay, so let's try and take these here, plug those into the original function. So what is f of 1, 1? What's f of negative 1, negative 1? So f of 1, 1, plug it in, you get 2. But if you plug negative 1, you also get 2. So is that the maximum? What is that? What do we have here? Is this a maximum or a minimum? We can't tell because they're the same value. So since they're the same value, I don't know if these represent maximums or minimums. I don't know. What I can do is I can just find any other point that lives here and plug it in here and see, or any other x and y value that make this true, plug it in here and see if it's bigger or smaller than 2. So let me just come up with the two numbers that will give me 1 here. So I'm going to do, how about this point? How about 4 and 1/4? If I do 4 for x and 1/4 for y, I get 1. Now what is f of that? So this point lives here. Plug it in here, you get, what, 16 plus 1/4 squared is 1/16. That's definitely bigger than 2. That means that these have to be minimums. And that means that there is no maximum, all right? And you can think about what this does. I mean, I can get bigger and bigger values here that would satisfy this. I could do like 10 and 1/10, and that would get bigger. I could do 100 and 1/100th, and that would get bigger. So these are, the minimum value of this function is 2. It happens at these two x and y values, and there is no maximum. So no max. All right. Just look at something here. I want to make sure that I didn't do that one in class, or the next one I do, I don't want it to be one I did in class. Okay, so I'm gonna do number 5 now. See, the issue on these is really kind of knowing when you've checked everything you need to check. All right, 5. And give myself some room because this is a lot of work in this problem. Now what we have is a function of 3 variables. 2x plus 2y plus z is the function of 3 variables. And our constraint is x squared plus y squared plus z squared equals 9. Something tells me I did this. Hold on. Okay, no, I didn't. Okay, good. All right, so I'm going to have 4 equations this time. First one, partial of f with respect to x has to be equal to lambda partial g with respect to x. Second equation, partial of f with respect to y must equal to lambda partial g with respect to y. Third equation, partial of f with respect to z must equal lambda partial g with respect to z. And the fourth equation is our constraint, so x squared plus y squared plus z squared equals 9. Now the partial of f with respect to x is 2. Lambda times partial g with respect to x, which is just 2x. And then partial of f with respect to y is just 2 equals partial g with respect to y times lambda, so lambda times 2y. And then partial of f with respect to z, which is 1, lambda times 2z, and then our constraint. And this cleans up a little bit here. I can do 1 equals lambda x and 1 equals lambda y. And over here, I can just leave it, or 1/2 equals lambda z. No, you know what? I'm going to leave it as 1. You'll see why. I'm going to leave this as 1 equals 2 lambda z. Because see, all these equations are all equal to 1, so I can set them all equal to each other. So let me start with the first two. If I start by setting equation 1 equal to equation 2, because they're both equal to 1, I get lambda x equals lambda y, which means lambda x minus lambda y equals 0. If I subtract, factoring out a lambda, I get lambda times x minus y equals 0, which means lambda equals 0, or x minus y equals 0, which would mean x equals y. All right, so let's start out by assuming this. Suppose lambda is 0. Then equation 1 would tell me what? Lambda is 0. 1 is 0? That doesn't happen. So lambda can't be 0. So I can chunk this. All right, suppose x equals y. If x equals y, then what can we do here? I could go into this equation and replace that with x, or sorry, replace that x with y. What can I do with the last equation? Suppose x is y. Let me do this. I can take this equation, since it's equal to 1, and set it equal to this one. And remember, I'm assuming that x is y. I get lambda x equals 2 lambda z. Move everything to one side. Lambda x minus 2 lambda z equals 0. Pull out a lambda, I get x minus 2z up to z equals 0. Which means lambda is 0 or x equals 2z. And we already know lambda can't be 0. So if x is equal to y, we also know x must be equal to 2z. So what I'll do now is I'll go into the third equation, and I'm going to try and get everything in terms of x. So I have x squared plus, now y is x, so that's going to be x squared again, plus z squared. So come to this equation right here, solve for z, half x equals z. Square both, you get 1/4 x squared equals 9. Now this is 2x squared plus 1/4 is 9/4 x squared equals 9, which means x squared equals 4, which means x equals plus or minus 2. So let's look at a couple of the different cases here. If x is 2, what's y? Well, y is x, so that. And then what's z? It's half of x, so 1. That's one possibility. -2 for x, then y, of course, has to be -2. And then half of -2 is -1. So those are this is your x, y, z. I should have put lambda in here. We can get lambda pretty easily. So this is x, y, z. Let's look at what lambda is. If x is 2, come over here. If x is 2, you can see that lambda is a half. If y is 2, you can see lambda is a half. And if z is 1, you can see lambda is a half. So you get 1/2 here. And then, of course, if x is -2, the only thing that changes is it's -1/2. So -1/2. All right. Okay, let's go back, make sure we got everything in order here. We set equation 1 and 2 equal to each other. Lambda had to be 0. We said it couldn't be that, but that would mean x has to be equal to y. And I think we've got everything we need here. Notice, because I never said, like, suppose x isn't 0 or something like that. Let's see. What number was this? Oh, 5. I was looking at the wrong one there. Yeah, that'll work. So now plug those into the original function. All right. Plug these into the original function. The x, y, and z, I get f of 2, 2, 1. We also look at f of -2, -2, negative 1. Let's see, if I plug in 2, 2, 1, I get 4, 4, that's 8, and 1, that's 9. And if I plug this in, I get negative 9. And so you have a maximum value of 9 and a minimum value of negative 9. So if you look at this function of 3 variables and you constrain it to that, which is actually a sphere, and you plug in points just on the sphere into this function, the biggest value you're going to get out is 9, the smallest value you're going to get out is negative 9. Now, what I'm trying to do is kind of give you a flavor of each of these. Number 7 is kind of a mess. I'll let you mess with 7 and 9 because that's part of what this course is. I'm just trying to give you some guidance here as to what you're supposed to do, but the algebra in number 7 is a bit messy. All right, let's move on to something a little different. So number 13, we have a function of 3 variables, f of x, y, z equals x plus 2y. That's it. There's no z in there. So z is free. And now you're given 2 constraints. So x plus y plus z equals 1, and y squared plus z squared equals 4. So we're trying to find the maximum and minimum values of this function constrained to 2 different equations. That's going to create a little bit of a different approach. So in our notes, let's see where I get into this. Where is it? I don't have it. That's interesting. Well, let's go ahead and work through it. Since I don't do it in the notes, but I'm sure I'm going to mention it in lecture, is that what we're going to do is of course, this is our f function. This is our g function right here. And this is now going to become our h function. And what we need is we need to find x, y, z, lambda, and mu such that the following is true. The gradient of f equals lambda times the gradient of g, that's the familiar part, plus mu times the gradient of h. So this is a constant in front of the gradient of g, and now we need to add a constant in front of the gradient of h. So this is going to look like this. Partial of f with respect to x, partial of f with respect to y, partial of f with respect to z must be equal to, I'll pass the lambda through here, lambda partial g with respect to x, lambda partial g with respect to y, lambda partial g with respect to z, plus pass the mu through, mu partial h with respect to x, mu partial h with respect to y, mu partial h with respect to z. And now, because when you add two vectors together, you add their components together. Okay, these will come together, and then I will set those equal to the 3 components here. So what I have, I'll write it up here. My first equation that I'm going to get is that the partial of f with respect to x must equal lambda times partial g with respect to x plus mu times partial h with respect to x. My second equation is partial of f with respect to y must equal lambda times partial g with respect to y plus mu partial h with respect to y. And then my third equation is partial f with respect to z must equal lambda partial of g with respect to z plus mu partial h with respect to z. And then my last two equations, equation 4 is x plus y plus z equals 1. And equation 5 is y squared plus z squared equals 4. So I have 5 equations and 5 unknowns. All right, so let's see how easy this is going to be. Hopefully it will be. Partial of f with respect to x is 1 equals partial of g with respect to x is 1, but then times lambda, so lambda. And then partial of h with respect to x, which is 0, because there is no x in there. So that's it. Lambda's 1. That's going to be nice. Partial of f with respect to y, which is 2, equals partial of g with respect to y, which is 2y, but then times lambda. Oh, no, sorry, this is g. Which is 1 times lambda, so lambda, plus mu times partial of h with respect to y, which is 2y times mu. So 2 mu y, like that. Okay, partial of f with respect to z, which is 0, equals partial of g with respect to z, which is 1 times lambda, so lambda, and then plus mu times partial of h with respect to z, so that's 2 mu z. And then these two equations stay. Now, this is nice. Lambda's 1. Know that right away. So I can replace 1 here, subtract 1 on both sides. So I get 1 equals 2 mu y. Over here, it's 1. Lambda's 1. Take it to the other side. Negative 1 equals 2 mu z. That looks okay. And how about we do this? How about we make this positive and make that negative? And then since these are both equal to 1, I'm going to set those two together. So if I set equation 2 equal to equation 3, I get 2 mu y must equal negative 2 mu z. Bring everything over to one side. 2 mu y plus 2 mu z must equal 0. Factor out a 2 mu y plus z equals 0. You get mu must equal 0 or y must equal negative z. All right, so let's take a look at these. What happens if mu is 0? Suppose mu is 0. Then look at equation 2. Equation 2 implies that 1 would be equal to 0. That's not true, so that can't be true, so that's not true. So that means that the only way this is all going to work out is if y is equal to negative z. So let's assume that. Suppose y is equal to negative z. Then what can we do? Look at equation 5. If y is equal to negative z, what I can do is I can go negative z squared plus z squared must equal 4. So that means we get 2z squared must equal 4, so z squared must equal 2. Z squared must equal 2, so z must equal plus or minus root 2. All right, so here's what I got so far. I've got that if y is equal to negative z, then z has to be plus or minus root 2. And that means that we could have this. We could have z being root 2, and that would mean that y is equal to negative root 2. Oh, I'm off the camera. Let me do it this way. I'm trying to find x, y, z, lambda, mu. I know that if z is root 2, that y must be the opposite, so negative root 2. I could also have root 2, negative root 2. But I've got to figure out what x would be, right? So I already know lambda's 1. That came from the very beginning, so that's not even something to think about. What would x have to be? So I could do that right here from equation 4. if y and z are opposites, right? If y and z are opposites, these cancel, and I just get x is 1. Either way, it doesn't matter which way I do it. That's nice. And then what about mu? Can I get mu? Where can I get mu? Right here. Solve that for mu real quick. You get 1 over 2y. 1 over 2y equals mu. So mu right here would be 1 over 2 times this, so negative 2 root 2. And then this one would be 1 over 2 root 2. That looks like, those look like my only candidates right there. Now really all I'm interested in are these. So now I plug those into the original function. Let me just double check this. What number was this, 13? Yeah. So if I plug in to the original function, f of 1 negative root 2 root 2, x is 1, y 2, so I get 1 plus, which is going to become a minus because I'm plugging in negative. So negative 2 root 2. And then if I do f of 1 root 2 negative root 2, this becomes 1 plus 2 root 2. And of course, this is going to be a max then. This will be a min. All right, I'll let you do 15. And that'll do it. I think that'll be it for this section. Good.